If a bowling ball and a baseball hit you with the same momentum, you will not describe those two experiences with the same word. And that's the first clue that momentum is not the thing your instincts think it is. Because your instincts want one number that means how bad it hurts, or how hard it hits, or how much damage it does. But physics doesn't hand you one magic number for that. Physics hands you different numbers that answer different questions. Momentum answers one kind of question. Energy answers another. Force answers another. And if you mix them up, you can do 100 collision problems correctly and still not know what momentum actually is. So let's do this the Feynman way. We'll start with what you can picture. Then we'll chase the confusion until it has nowhere left to hide. And only then will we say what momentum is in a way that makes it feel almost inevitable. Here's a simple experiment you can run in your head. You're sitting on a rolling office chair. You have a heavy backpack in your lap. You shove the backpack forward. What happens? You roll backward. That's not a special trick. That's not because momentum is conserved as a slogan. That's something you can feel in your stomach. You push something one way and you go the other way. Now imagine you do the same thing, but with a light pillow instead of the backpack. You still roll backward, but not as much. Already your brain starts to make a guess. Maybe the amount of rolling backward depends on the mass of the thing you threw and how fast you threw it. That's a good guess, but it's not the deep point yet. The deep point is this: nothing magical happened. No invisible spring in the floor fired you backward. The only forces were between you and the object, inside the system, and yet the whole system rearranged its motion in a very strict way. That strictness is what momentum is about. But before we get there, we have to clean up a mess. The mess of thinking momentum means hit power. Let's build a mental lab. 2 objects, 1 quick collision, and your brain trying to predict which one wins. Picture a baseball and a bowling ball rolling straight toward your foot. Let's say, just for the sake of argument, that each one has the same momentum. The baseball is light, so it must be moving fast. The bowling ball is heavy, so it must be moving slow. Same momentum. Now, which one would you rather have hit your foot? Everybody chooses the baseball, and you don't need a physics degree to see why. So if they have the same momentum, why do they feel so different? That question forces you to face a truth. Momentum is not a direct measure of pain or damage or impact severity. So what is? Well, sometimes what you're really thinking of is energy. Kinetic energy grows with the square of speed. That means a light object moving very fast can carry a surprising amount of energy, and a heavy object moving modestly can also carry a lot. But the relationship is different. One scales like velocity squared, one scales like velocity. If you keep momentum fixed and make the mass smaller, the speed has to rise. When speed rises, energy rises sharply. So the baseball with the same momentum as the bowling ball can actually have much more kinetic energy depending on the numbers. That could suggest the baseball should be worse, not better. Yet your intuition says it's better. So now you're confused in the opposite direction. Good, that's where learning starts. The missing piece is that how bad it hurts is not just about momentum or just about energy. It also depends on how the collision happens, how long it takes, how the force is distributed, what deforms, what breaks. A bowling ball doesn't just deliver momentum, it delivers it with a small contact area, little deformation, and a stiff interaction. The baseball squishes, spreads the force over time, spreads the contact area, and can bounce in complicated ways. So your foot is not measuring momentum. Your foot is measuring a complicated combination of peak force, duration, pressure, and how tissues deform. That's not a failure of physics. That's physics telling you, ask a precise question, get a precise tool. Momentum becomes the perfect tool when the question is not how much does it hurt, but how does motion get redistributed when things push on each other? To see why, let's do a different collision, one where your intuition about damage is irrelevant. Take 2 identical carts on a track. One cart rolls in and bumps the other. Nothing breaks, no drama. You just want to predict what happens next. You want a clean rule. Here's the thing your professor probably told you. Momentum is conserved, so you can solve it. But that leaves you with a bad taste because it sounds like, because the textbook says so. Instead, let's make it unavoidable. Here's the first scandal. An object doesn't own its momentum the way it owns its mass. Momentum depends on what you're comparing it to. If I say a car has a velocity of 30 meters per second, you should ask, relative to what? The road. The Earth, the center of the galaxy. Another car. Momentum is the same way. Momentum is not a sticker you can attach to an object in isolation. It's a number you assign once you pick a reference frame. That sounds like a nuisance, but it's actually a clue. Momentum isn't trying to be a mystical substance living inside things. It's a bookkeeping number that helps you track motion in a chosen frame. And now comes the second scandal. The most powerful momentum statement is never about one object. It's about the total momentum of a system. When people say momentum is conserved, they don't mean this one object keeps its MV. They mean if you choose a system where no outside forces give a net push, then the total momentum of everything in that system stays the same over time. So momentum is not primarily a property, it's a constraint. Let's return to the rolling chair experiment. Why did you roll backward when you threw the backpack forward? Because inside the system, chair plus you plus backpack, there was no external horizontal force doing a net push. The floor's friction is small enough that for a quick shove we can ignore it. So the only forces were between you and the backpack. You pushed the backpack forward. That force acted on the backpack. But by the nature of interactions, the backpack pushed you backward with an equal and opposite force. That statement is Newton's third law in everyday words. Forces between two bodies come in opposite pairs. Now here's the move that makes momentum feel inevitable. Imagine we watch the backpack's momentum. While you are pushing it, a force acts on it for some time. That changes its momentum. The amount of change depends on how strong the force is and how long it acts. That's not a philosophy. That's a measurable relation. Force changes momentum. In calculus form, it's the cleanest way to write Newton's second law. The net force equals the time rate of change of momentum. But you don't need calculus to feel it. If you push harder, the object's motion changes more. If you push for longer, the object's motion changes more. Now look at you. While you push the backpack pushes you backward with the same magnitude force for the same time. So your momentum changes too, by the same magnitude but opposite direction. One momentum goes up, the other goes down by the same amount. The sum stays the same. That's it. That's conservation of momentum in its simplest skeleton. It's not a separate law floating above Newton. It's a consequence of how forces work when interactions are internal. Let's do it slowly because slow is where the meaning lives. Consider two objects, A and B, interacting. No outside forces, just them pushing each other. Object A experiences a force from B. Object B experiences a force from A. Those forces are equal in magnitude and opposite in direction. During a short time interval, those forces change the momenta. The change in momentum is proportional to the force times the duration. Same force magnitude, same duration, opposite directions. So the change in A's momentum is the negative of the change in B's momentum. When you add them, the change S cancel. Therefore, the total momentum doesn't change. That's conservation, not as a slogan, but as arithmetic. Now notice what we did. We didn't solve the detailed contact forces. We didn't model how the backpack compresses your hands. We didn't track every molecule. We just used the symmetry of interaction. If the forces are internal, they come in pairs. That's why momentum is the hero in collisions. Collisions are messy, lots of forces, lots of deformation, short times. But momentum doesn't care about the details if you draw the system boundary correctly. Let's test that idea with the classic problem everyone remembers. A bullet embeds in a block and the block swings like a pendulum. If you try to solve that with energy for the entire event, you get stuck because the bullet heats up the block, deforms it, makes sound. Kinetic energy is not conserved in that inelastic collision. It changes form. But momentum, over the short collision time, external impulses like gravity are small compared to the huge internal forces between bullet and block. So you can treat the bullet plus block system as isolated for that brief interval. Momentum is approximately conserved during the collision itself, and that lets you find the speed right after impact. Then, after the collision, you can use energy to analyze the swing, because during the swing the forces are conservative enough and the deformation is mostly done. So momentum is not the only conservation law. It's the right conservation law for the right slice of time. That's already closer to what it actually is. Momentum is the quantity that survives the chaos of internal interaction. but we can go deeper. A lot of courses define momentum as mv and stop there. They treat conservation as a trick. You plug into equations, you get numbers, you move on. The deeper idea is that momentum is the universe's way of keeping track of who pushed whom without caring about the microscopic details. To see that, we need to think of momentum as a ledger. Imagine you're running a household budget. You have a shared bank account. Money can move from one family member to another, buying groceries, paying rent, but inside the household you can't create money from nothing. If the account balance changes, money must have come from outside or gone outside. Momentum in an isolated system behaves like that shared balance. One object can give momentum to another through forces, collisions, tension, springs, but the total doesn't change unless an external force provides an impulse. So momentum is a kind of motion currency. Now you might say, but I can make an object stop. Doesn't that destroy momentum? No. You can make an object stop by giving its momentum to something else, the earth, the wall, your hand, the air. We often ignore those recipients because they're huge. The earth barely moves when you stop a ball. But that doesn't mean it didn't take the momentum. It means you didn't notice the earth's tiny velocity change. This is one of the most honest lessons physics can teach. The bookkeeping doesn't care whether you notice. If momentum seems to disappear, it went somewhere you didn't. So measure. And that leads to a powerful diagnostic question you can ask in any situation. If total momentum changed, what delivered the external impulse? That question is like turning on a flashlight in the dark. It forces you to identify the outside agent, friction, gravity, a rocket engine, a wall. Now let's build another thought experiment that makes momentum feel less like a formula and more like a necessity. Two people stand on frictionless ice. They face each other. One throws a medicine ball to the other. The thrower slides backward. The catcher slides backward when they catch it. Then they throw it back. You can track what happens without numbers if you think in momentum. The medicine ball carries momentum across space. It's like a messenger. The moment you throw it, you've transferred momentum from your body to the ball. When your friend catches it, the ball transfers that momentum to your friend. In other words, momentum is something that can be transported. Now, if you really want to make this vivid, imagine you have a long, weak spring connecting you to your friend. You pull on it, you feel a force, but nothing is touching directly. Something is transmitted through the spring. The spring's tension acts as a channel that transfers momentum between you. A force is not just a number. A force is a mechanism for exchanging momentum. That sounds like wordplay until you realize it's how we understand everything from billiards to rockets. A rocket doesn't push on space. It throws mass backward at high speed. That exhaust carries momentum. The rocket gains equal and opposite momentum. The total stays consistent. So momentum is the currency that lets you talk about motion exchange in a way that doesn't depend on the ugly details. Now we should address a crucial subtlety. The definition P equals mv works in everyday speeds, but it's not the full story. At high speeds, close to the speed of light, the momentum formula changes, and yet the conservation principle survives. The universe still keeps that ledger. That should make you suspicious in a productive way. If the formula changes, but the conservation stays, then maybe the essence of momentum is not mv. Maybe mv is just one expression of a deeper thing. So what is that deeper thing? Let's go back to Newton's second law in its clean form. Force equals the rate of change of momentum. This makes momentum the quantity that force changes. In other words, if you want a definition that is operational, based on what you can measure, you could say momentum is the thing that accumulates when you apply a force over time. That accumulated push is called impulse. Impulse is not a new mystery. It's literally the change in momentum. Think about catching a fast ball. You can catch it safely by moving your hand backward as you catch it, increasing the time over which you bring the ball to rest. The ball's momentum changes from forward to zero. That change is fixed. But by spreading it over more time, you reduce the average force. So momentum is what you must change to stop or redirect an object. And the difficulty on this, if changing it, is the physical meaning we often describe as inertia in motion. Mass is inertia against acceleration. Momentum is inertia in motion. But we still haven't hit the most profound part of actually is. Because there's a deeper question hiding under every conservation law. Why do these conserved quantities exist at all? Why does the universe allow energy conservation, momentum conservation, angular momentum conservation? Are these just lucky patterns we observed? Here's where we step into one of the most beautiful ideas in physics: symmetry. Not symmetry like a butterfly wing, symmetry like the laws don't change when you do a certain transformation. Now, for the part that rarely gets said out loud, momentum conservation is what you get when the universe refuses to care where you do the experiment. Let that sink in. Imagine you do a collision experiment on this table. Then you pick up the whole apparatus and move it 1 meter to the left and do it again. Do you expect the outcome to change just because you moved it? No. If the laws of physics are the same here as they are 1 meter over there, then the equations describing the system don't depend on absolute position. They depend on relative positions and interactions. That statement, the laws are the same everywhere, is translation symmetry. And translation symmetry has a consequence. A quantity is conserved. That quantity is momentum. You don't have to know the formal theorem to appreciate the logic, but it helps to see the shape of it. If the laws don't depend on where you are, then shifting your whole system in space shouldn't change the physics. That means there's a kind of invariance built into the structure of the laws. And whenever you have that kind of invariance, there is a charge, a conserved thing, that goes with it, like a shadow cast by symmetry. Momentum is that charge for translations. So momentum is, in a deep sense, the universe's translation bookkeeping. It's the number that stays fixed because space is uniform. If space were not uniform, if the laws changed from place to place, momentum wouldn't generally be conserved. That should make you look at momentum differently. It's not a random invention. It's a fingerprint of how the universe is built. Now you might worry, wait, gravity depends on position. Doesn't that mean space isn't uniform? Good question. Gravity from a planet is not a property of the laws changing. It's a property of a particular physical situation. There is a planet here, not there. The underlying laws can still be translation invariant in a broader sense, but the presence of a localized mass breaks that symmetry in the situation. That's a subtle distinction. The laws can have a symmetry even if the particular setup doesn't. And that distinction helps you understand something practical. In a gravitational field near Earth, momentum in the vertical direction is not conserved because there is an external force. But in the horizontal direction, if we ignore friction, it is approximately conserved because there's no external horizontal force. So even in everyday life, the symmetry idea is whispery. Saying to you, look for directions or conditions where the external influence is absent. Now let's tie it all together so the title's promise is actually fulfilled. So momentum isn't a mysterious stuff inside objects. It's the conserved bookkeeping number that tracks how motion can be redistributed without outside influence. In everyday low-speed physics, that bookkeeping number is mv. That's the simplest expression. But the deeper meaning is, momentum is the quantity that the universe won't let internal forces change. It's the constraint that allows you to predict the motion of complicated systems without solving every internal detail. And it's conserved because of something even bigger, the uniformity of space. The fact that doing physics over here is the same as doing physics over there. Once you see momentum this way, a collision stops being a trick problem. It becomes a question about boundaries. What system are you considering? What's inside? What's outside? What external impulses can sneak in? If you include the right things inside the boundary, the total momentum becomes a calm, steady number. Even while inside the boundary, there can be chaos. Think about a firecracker exploding midair. Pieces fly everywhere. It looks like momentum is being created because suddenly there's motion where there wasn't. But if the firecracker was initially at rest, the total momentum was zero. After the explosion, the pieces have momenta that add to zero. They fly apart in opposite directions with a strict balance. The explosion didn't create net momentum. It redistributed momentum internally because the internal forces were huge but opposite in pairs. That's momentum as a truth serum. It tells you what internal mechanisms can and cannot accomplish. Internal mechanisms can create energy in new forms, chemical to kinetic, for example. They can create heat, sound, deformation, but they cannot create net momentum from nothing if no external impulse acts. So if you ever see a system take off in one direction without throwing anything the other way and without interacting with the outside, you should be suspicious. Either you missed an external interaction or your model is incomplete. Now let's leave you with a final lens you can use forever. Once you see momentum this way, every collision stops being a plug and chug problem and starts looking like a test of what the universe considers outside. And that's what your professor may not have told you, not because they were hiding it, but because courses often rush to computation. Momentum is not mainly mv.mv, is the convenient face it wears at low speeds. Momentum is the conserved motion ledger of an isolated system, the quantity that forces trade between parts, the thing whose conservation is rooted in the uniformity of space. And if you want to feel it, not just memorize it, sit on that rolling chair, throw something, and notice what the universe refuses to let you get away with.